Today we will be talking about the real number system. I would try to tell you what essentially is the real number system, what are real numbers, and why do we need them, and hence we will try to classify them. So, why do we need real numbers and why numbers at all? Well, simple answer is they help us count. They help us count and they help us measure. Real because they are very real. They're a part of our lives. We all the time without even realizing that we're using real numbers. Another way of understanding real numbers is that perhaps the numbers which are not unreal or imaginary, they are real numbers. So why do we need real numbers? We are human beings. It's our basic requirement. We like to measure, we like to compare. And when we are doing that, when we are comparing, when we are measuring, what makes it a simple process is using numbers. What numbers? The real numbers. So as I just said that real numbers, you can also think in terms that excluding all the unreal numbers or imaginary numbers, which we often call complex numbers, everything is real. So in mathematical terms, I can also say that a number whose square as in the number getting multiplied by the same number again. So x multiplied by x square is either positive. When I say positive, it means strictly greater than 0, or it is 0. That is, any number, if you make a square of it, if it is strictly greater than 0 or it is equal to 0, is a real number. You can always keep this definition in your head. In case x is equal to minus of some number, say minus 10, this is unreal. Because logically, when you have a real number and you, be it a positive real number or a negative real number, when you multiply it by itself, it must be positive. If that's not happening, then it's not a real number. Well, now let's try to classify real numbers. So when I say let's classify real numbers, that means we will in detail try to talk about what makes the set of real numbers. What makes the set of real numbers? So symbols, as you can see here, I've written some symbols here. So this symbol stands for real numbers. Real numbers. So if I may say that this entire circle, the big circle that I have here, is real numbers, set of real numbers, then the next thing I will talk about here is the symbol Q, which is the set of rational numbers. We call them rational numbers. And then I'm going to talk about something called integers, whole numbers, and natural numbers. And of course, what you can see here is also something called irrationals. So irrationals also are there. Now, how they are there, what is the composition like, that's what we will try to understand right now. So you have a set of real numbers. What makes real numbers? The first thing that I'm going to talk about, and which comes very naturally to us, is the set of natural numbers. The set of natural numbers. Now, the set of natural numbers are basically counting numbers, the numbers that we use to count. If, say, you have few pencils, you would like to count them. 1, 2, 3, 4. Counting starts with 1. So counting numbers are your natural numbers, and clearly they are real in nature. So they are a part of, natural numbers are a part of real numbers. So natural numbers is right here, set of natural numbers. What are natural numbers? As I mentioned, they are the counting numbers. Counting numbers. They are the easiest to understand, and that's the reason why I am starting classification with natural numbers, because we count every time. The easiest way to understand real numbers is natural numbers. Natural numbers are real. For example, suppose there's a farmer who's got some sheep and he has to take them out for grazing every day, every single day. So when he's taking his sheep, he must be counting that he's got this many number of sheep. And when he's coming back, he would definitely count that he should not be missing on any of the sheep, right? So counting is an essential part of our lives. Counting must have been essential since ages, right? Counting numbers are called natural numbers, and counting generally starts with 1. Now, let's take an example close to our lives. So, suppose you're a group of 10 friends and you all have taken up some exam. Now, you must have scored some marks in this exam, and you want to rank amongst yourself that who got the highest marks, who got the least marks. You would start counting the ranks according to the marks. Some A person is first according to the highest marks he must have scored or she must have scored. Similarly, positions second, third, fourth. What are we doing? We are counting. We're counting the positions. So when they would rank each other, the ranks would be as following: first rank, second rank, third rank, so on and so forth, till the 10th rank. So you can think in terms of rank also, you can think in terms of head count also. That's what is natural number. So natural numbers start with 1 because this kind of counting starts with 1. So natural numbers flow like this. So your natural numbers start with 1. You have 1, then comes 2, then comes 3, then comes 4, so on and so forth. They go on and on and on. We can quote n for some nth term, and then again, there's no stopping to it. They go on and on and on. I would talk about infinity after some time in some other lecture, and there we will again pick up this topic. A very important number in our lives, 0. So 0 is an important number. And what is this paradox of 0? Is really 0 required? Is it really a number? Because see, counting starts with 1, 2, so on and so forth. We never start our counting with 0, 1, 2, 3, 4. We start with 1, 2, 3, 4. So why is 0 required? Because you counted balls and you start putting them in 4 boxes you had. Without realizing, you are finished with all the balls by the 3rd box. And the 4th box is empty. Empty. So, if I may now ask you, how many balls are there in the 4th box? What will be the answer? The answer will definitely be 0, right? So here comes the importance of 0. It's the count of balls in the 4th box. It is 0, and that's signifying that the 4th box is actually empty. I'll give you a very layman example also out here. Suppose your mother is preparing breads for you guys, and you're 4 of you in the family. And your mother knows that everyone takes 2 breads at a time. So that means she's going to make 8 breads. By the time she comes to the table, all 8 breads are gone and she is left with nothing for herself. So how many breads is she left with? 0. So that's what the number 0 signifies. And when you add 0 to the set of natural numbers, to your counting, when you add this number 0 to your counting, it gives you a new set, which is the set of whole numbers. So what are whole numbers? Whole numbers are basically natural numbers plus another number, which is 0, which is signifying emptiness. Okay. So set of whole numbers denoted as W. N and 0 together make the set W. Together make the set W. Next, I'm going to talk about extending whole numbers. Next, I'm going to talk about integers. So let's talk about integers. The set of integers, which is denoted as Z, set of integers. Now, what are integers? Integers are whole numbers, 1, 0, 1, 2, so on and so forth. When you add the negatives, this becomes a set of integers. So, negatives of all the positive numbers count that you have, natural numbers, including 0, so that is whole numbers, and the negatives of every natural number would create the set of integers. Why do we need negative numbers? We need negative numbers for a purpose. Suppose you had lent $80 to your friend. You have lent $80 to your friend, and now she is returning to you $100. Of course, it's a fair friendship and there's no interest or anything on what one person is lending to the other. So keeping that in your mind. Now that means what has happened? You gave her 80 and she has given you 100. So you are indebted by $20, which is kind of the idea of negative numbers, deficit. So that's the kind of idea of negative numbers, and that's why negative numbers are important. Integers are basically all whole numbers and including the negative numbers. Now the truth is that we cannot just think of numbers in terms of integers or whole numbers or natural numbers. So comes into picture the rational numbers. Now, what are rational numbers? They're fractions. You cannot take time always in terms of integer or natural number. For time, for height, there are many, many measurements for which fractions are important. So, rational numbers are essentially those numbers which are fractions or decimals. Example, time. Let me give you an example in terms of time. Suppose you are supposed to meet your friend at, say, 3:30 in the afternoon, and you are leaving your place at 3, and you give her a call that I'll be meeting you in half an hour. That's how we speak, right? We will meet you in half an hour or 30 minutes, but many a time, most of the times, we'll just say that we'll meet you in half an hour. This half, what is this? It's a fraction of time. That's why rational numbers are important. Why would you say that I'll see you in half an hour? Because 30 minutes, you'll be meeting her in 30 minutes. In 30 minutes. And 30 minutes out of 1 hour, that is 60 minutes. 30 minutes out of 60 minutes is equal to 3 by 6 or is equal to 1 by 2. So half of an hour. Half of an hour. 30 minutes out of 60 minutes or half of an hour. That's what is a rational number. So fractions or rational numbers. So fractions, my friends, fractions are the numbers which could be displayed as P upon Q, where P and Q both are integers, and Q should not be equal to 0. And Q should not be equal to 0. This, when P by Q cannot be expressed as an integer, and of course, this is the situation where P by Q and P by Q cannot be expressed as an integer. then it is called a rational number or a decimal value. It will become a decimal value. So rational number is any number which is written in the form p by q, where p and q are integers and q should not be equal to 0. When we are talking only about fractions, then we have the case that it has to be p by q, and p by q, we are not able to express it as an integer. Then that is a fraction. Now a decimal value like 2 upon 4 is basically 1 by 2. And in terms of decimal system, it is 0.5. 2 upon 3, if you take the fraction 2 upon 3, this is also a fraction. 2 and 3 both are integers, but I cannot express 2 by 3 as an integer. So this is a rational number. What kind of a rational number it is? If you will write it in the decimal form, you are dividing 2 by 3, you will get 0.66666, so on and on and on and on. It's a never-ending sequence of 6 that you will get after this decimal point. This is called a terminating decimal, and this is called a non-terminating decimal. Whether it is a terminating decimal or a non-terminating decimal, it is a rational number, because whether it is terminating or non-terminating, I will be able to write it down as a fraction. I will be able to write it down as a fraction. So it is a rational number. So both could be rational numbers. Now, why I am actually talking about the decimal system here is for a reason that when you jump from one rational number to another rational number, then there you can actually have some other kind of numbers also. We will think in terms of decimal first. Let me give you the decimal value of pi. When I try finding out the decimal value of pi in my computer, I got the value from the calculator 3.14159265359. It stopped after that, but ... there can be many more here. So what you can notice out here is something. The numbers of the decimal, they do not have any pattern. They do not have any pattern. Like you have a pattern here. In the non-terminating decimal, you have a pattern here, which is not ending. But here, you don't have any pattern here. These kind of numbers are called irrational numbers. But they're real in nature. But they are also, they're not imaginary numbers. They are real numbers. They exist. Pi exists, okay? They are irrational numbers. Pi exists. E exists. They are examples of irrational number. And why they exist? I'll give you a simple reason why they exist. Very simple reason. If you take a right-angled triangle, with the dimensions, isosceles triangle with the dimension 1 unit and 1 unit here. This is the hypotenuse. We all know Pythagoras theorem, right? And the hypotenuse will be equal to square root of 1 square plus 1 square. That is square root of 2. Square root of 2 is an irrational number. It's not imaginary. It's an irrational number. It is real. It is real in, this is a live example that it's a real number. It exists, okay? It's not that we're just thinking in our head. It does exist. Root 2 exists, and it is an irrational number. So now I'm going back to the diagram that I showed you, and let's fill it in now. A picture of this diagram in our head. The first thing I want to mention here With examples, let's try to understand which would be a bigger chunk of numbers, which would be a smaller chunk of numbers. Let's try to understand that. And I'm going to start with rationals. So if you notice 5, the number 5, it's a natural number, right? I can write it down as 5 upon 1. When I write it down as 5 upon 1, then what is happening? I am actually able to represent 5 as P by Q, as P by Q, where P is an integer and Q is also an integer. And this time we are actually able to write it down just as an integer, 5, or a natural number 5. So when we talk about rationals, now I'm going to just modify the definition of rationals. Earlier, we worked on fractions. I was trying to tell you that fractions are rational numbers, which we cannot represent as an integer. But it's not just the fractions which are rational numbers, also the integers which I can represent in the form of P by Q. They can be called rational numbers because I do have a fraction representation for them. So as I mentioned, integers. This is an example of a natural number. The natural number and whole number, they only differ from each other. The only difference is 0. I can write down 0 as 0 upon 1. I can write down 0 as 0 upon 1 because anything multiplied by 0 will always give you 0. Anything multiplied by 0 will always give you 0. So you can write it down as 0 upon 1, 0 upon 2, anything. Or the simple way to write it down is 0 upon some number and you will get 0 only. So again, you are able to write it down in terms of P by Q, where 0 is not an integer, but the representation is there. So therefore, all the whole numbers are also, you can say, they're rational numbers. Yes, my answer to the question that is 0 a rational number is yes. 0 is a rational number because we do have a representation. We do have a Q denominator for 0 also. Next is, so natural numbers, whole numbers, and then comes integers. The way you had 5, you can take minus 5 and you can represent minus 5 upon 1. So yes, all the integers, be it positive or negative, could be represented in terms of P by Q. Again, they are rationals. So set of integers is very much inside the set of rationals. Set of whole numbers is very much inside the set of rationals. Set of natural numbers is very much inside the set of rationals. So what essentially is happening? Set of natural numbers, if you may notice, is the smallest of all here because it starts with 1 and goes on and on. If you add another number 0 to it, you get a bigger set because it has one additional number, and that's the set of whole numbers. If you add negatives, you have more numbers now in the set. So the bigger set would be integers. And if you just realize with the examples that I gave you, set of rational numbers include all fractions. It includes integers, whole numbers, natural numbers, everything. So which is a bigger set? Set of rational numbers. And if you include all the rational numbers and irrational numbers, you get the set of real numbers. So the set of real numbers is, of course, the biggest. It would also include irrationals. Then comes set of rationals, which is smaller than real numbers. The only difference is actually irrational and rational. So actually, in this portion, you will have irrationals basically, which are making it the set of real numbers. Then inside the rational numbers, you have all the integers. And inside all the integers, you have all the whole numbers. And inside all the whole numbers, you have natural numbers. So that's how this relation would flow. In nutshell now, the classification of real numbers, I can say that real numbers are a union of all the rational numbers and irrational numbers, which we write down as Q complement. Because whatever is not there in the set of rationals is there in irrational as long as it's a real number. Thank you.